Here's problem 518. Two blocks in contact with each other are pushed to the right across a rough horizontal surface by the two forces shown. If the coefficient of kinetic friction between each of the blocks and the surface is 0.3, determine the magnitude of the force exerted on the 2 kilogram block by the 3 kilogram block. Let's name the 2 kilogram block M1 and the 3 kilogram block M2. And we're told that the coefficient of friction between these blocks and the surface is 0.3. No units on that. It's just a number, 0.3, which means that the frictional force is 30% of the normal force. And we're told it's a rough surface, so we do know there's friction. That's our key to knowing that there is friction present. So one of the first things we want to do for any of these kinds of problems is a free body diagram. And let's do a free body diagram of the whole system, M1 plus M2. If I made a free body diagram of the total system, and the reason I want to do this is then the internal force between the two blocks is just that, internal to the system, it's part of the system, and they are no longer external forces to worry about. So we have a 30 Newton force on the left, and we have a 10 Newton force on the right. Of course, there'll be weight equal to the total mass times g, and there will be a normal force, and there will be a frictional force against the sliding motion. Now, since the 30 newtons is greater than the 10 newtons, this frictional force will be against the motion, and it'll be equal to mu times the normal force. And as a result of all these forces, it will manage to accelerate in the positive x direction. So that is our free body diagram for the total blob of the mass 1 with mass 2. Now we want to figure out this frictional force, and to find that we need to find this normal force. So let's look first at the vertical direction. We will have that the summation of all the forces in the y direction is equal to 0 because there's no acceleration in that direction, and that is equal to the normal force minus the total weight m1 plus m2 times g. So that means that the normal force will equal m1 plus m2 times g, the total weight, and that would be equal to 2 plus 3 times 9.8, 5 times 9.8, which would be 49 newtons. That is our normal force. We want to find that because that will give us the frictional force. The frictional force would be equal to mu times the normal force, 0.3, if I can make a 3 here, times 49 newtons. And 0.3 times 49 newtons is 14.7. So the frictional force is 14.7 newtons. Alright, so we know all the forces in the x direction. If we set up Newton's second law in that direction, the summation of all the forces in the x direction will be equal to the total mass times a, and that will be equal to 30 minus 10 minus the frictional force. So we're going to have that mass 1 plus mass 2 times the acceleration will be equal to 30 minus 10, which would be 20, minus the frictional force, which we just determined to be 14.7. So we're going to have 2 plus 3, or 5, times the acceleration will equal 5.3, or the acceleration is going to equal 5.3 divided by 5, or 1.06 meters per second squared. And it will be going to the right like that. This is all nice to know because we know for this blob that the acceleration is 1.06 meters per second squared, but that will also be the individual acceleration of each block. We want to find the contact force between the blocks, so we have to go more internal. Let's do a free body diagram of mass 1 to 2 kilograms. Now we know there's weight acting on it, so that'd be equal to m1g, and there would be a normal force, let's call it n1, and they're canceling out in the vertical direction. We do know, looking at the original diagram, that there's a 30 Newton force pushing on this on the left-hand side. But what's happening on the right-hand side? Well, there's some kind of reaction force of the 3 kilogram block pushing back on the 2 kilogram block, and we'll just call that P. We don't consider the 10 Newton force because that's actually acting to the right of the mass 2, the 3 kilogram block. So it's not acting directly on the mass 1, 2 kilogram block. As a result of all these forces, there's an acceleration to the right, which we have found to be 1.06 meters per second squared. This is our free body diagram of mass 1. We want to find, oh no, we forgot one more force. Friction. We have a frictional force that's called F1 that's going to the left, and this F1 would be equal to mu times N1, the normal force. Let's find that normal force. Looking at the vertical direction, the summation of all the forces in the y direction is equal to 0. There's no acceleration in the y direction, and that's going to be equal to N1 minus M1g. So our normal force is going to equal M1g, and that's going to equal 2 times 9.8, or 19.6 newtons. Hence, our frictional force is mu times the normal force, this is N1, and that's going to equal to 0.3, because mu was given as 0.3, times 19.6, and so our frictional force, 0.3 times 19.6, is 5.88 newtons. Okay, if we look at the summation of the forces in the x direction, that should equal our mass times acceleration, m1a, and that should equal the net force in the direction of acceleration. So the acceleration is our positive direction. So we're going to have, we got 30 Newton force going to the right, we've got a P force going to the left, so we're going to go minus P, and we got a frictional force going to the left, so we're going to have a minus F1. So we have that 2 times A is equal to 30 minus P minus our frictional force, which was 5.88. Let's bring the P over to the left and bring the 2A over to the right. So our pushing force P is equal to 30 minus 5.88 minus 2 times the acceleration, 1.06. So this would be 30 minus 5.88 minus 2.12. So 30 minus 8, which will give us 22 newtons. So the pushing force of block 2 on block 1 is 22 newtons, and for that matter, the pushing force of block 1 on block 2 is also 22 newtons. They're equal and opposite according to Newton's third law, and so they should have the same magnitude. But this is the force that we were asked to find, 22 newtons.